Okay, as promised, I made up another compound linear example doing the reversal of the inequality. So the first thing we're going to do is we're going to remove the middle term here, or the constant added to the middle here, and I'm going to add the opposite to both the left and the right sides. So 6 minus 3, which gives me 3, which is greater than a negative x, which is greater than or equal to a positive 1. Now I need to remove the numeric coefficient, which remember that numeric coefficient is a negative 1. So I'm going to multiply by the reciprocal, which of course looks like division because it is, on each part, right? Left, right, and center. And when I do that, the inequalities reverse. So I will go from having greater thans to less than symbols. And now I have a negative 3 on the left. In the middle I have my positive x, and on the right I have my negative 1. And that is my left endpoint, which is a negative 3. And so I locate my negative 3. I'll put a left parenthesis on it, and then I'll go locate my right endpoint, which is a negative 1. And I'll put my right bracket on it because it is included, and then I'll draw a line between those. Interval notation, negative 3, comma, up to negative 1, and left endpoint not included, parenthesis, right included, so it has a bracket. And you'll notice that even though this started out looking wrong to us, right, with the greater than symbols, that when it ended up, it was all fine. So don't make snap judgments on those compound inequalities. Compound inequalities also can have that reversal of the sense of the inequality, and you've got to just work through it unless you're going to solve them in two parts, and we did see how difficult that can be. All right, let's move on now to Lehman's example or exercise number 80 on page 300 of his text. So looking at this example, it says Toyota Prius sales in the United States are shown in the table 61 for various years. And our years and then sales in thousands of cars are being given. So let F of t be a Toyota Prius sales in thousands of cars for the years. So F of t, the thousands of cars sold according to the year since 2000 is going to look like F of t being 30t and then minus 59.33. There's our linear equation that's going to describe this model. And it says, A, what is the slope of this model? Well, our slope of this model is the rate of change, right? And the rate of change is the numeric coefficient of the independent variable. And so our rate of change is 30. So m is equal to 30. And what does this mean? Well, it's 30, and our dependence units, this is thousands of cars, so thousands of cars, and this is per year. So this is an increase of 30,000 cars per year. So 1,000 cars per year. And that's what that means, is that every year, after 2000, that the number of cars sold is going to go up by 30,000. Now part B says, in which years will the sales be more than 30,000? And this is where our inequality comes in. So F of t, when will our sales, right, be more than 340,000, and that's what we're going to be looking at. So F of t is what this is right here, right? That's F of t. So I'm going to put that on the left, and then greater than 340. You see how it becomes a substitution. Okay, so you see the first thing we did was a translation problem. The years in which the sales are more than 340,000, and so I substituted in for the F of t, which is our expression, and then I solved it. I took the liberty of solving it, and I came up with t is greater than 13.333. So this is after 2013. It's a quarter of the way essentially into 2000, or 4 months into 2013. So the year that it'll be more than 340,000 cars, we have to say, is in 2014. And that's how we interpret that meaning of something with a decimal point. And again, t is greater than 13 years, meaning we add 13 to 2000.